on section 3.4 in your lesson or textbook. And this is really exciting because I think it's been a while since you've done any trig, right? And so we don't want to go too long without doing trig. And you were probably wondering, okay, I can take the derivative of 3x squared plus 7x plus 12, no problem. I can take the derivative of all different kinds of polynomials. I even learned the quotient rule and the product rule, and I learned about e to the x. That was the other great thing you learned. Robinson, what did you learn about e to the x?
The derivative is e to the x.
Right, and you thought that was awesome? Okay, maybe you're not a nerd. All right, so it is awesome. It's really, really, really good. But anyway, so now you know e to the x. You don't know the derivative of a log function, but I'm not going to tell you today. You know the derivative of, well, that's about it. So let's learn the derivatives of all the trig functions, right? And if we wanted to know a derivative, how would we go about it? Like if we just had a function, oh, wrong button, sorry. If we had a function, f of x, and our function was equal to the sine of x, how would we go about finding the derivative? How are you going to do that? What did we learn in the last section? I mean, the last chapter. The definition of the derivative is the limit as f of x plus a, yada, yada, right? Okay, so we have that f prime of x would have to be the limit as h goes to 0 of f of x plus h minus f of x all over h, right? So here, this would be the limit as h goes to 0 of sine of x plus h minus the sine of x all over h. Okay. Now, don't be crazy, right? You know that the sine of x plus h is not the sine of x plus the sine of h. You remember that there is a rule for the sine of x plus h. So I'll just write that real quickly. Let's recall. And this is on your trig sheet, which you can access on the computer if it was like additional, I see somebody has it, so additional resources maybe. The sine of x plus h, or in general, how about the sine of a plus b, is equal to the sine of a sine, oh, is it sine cosine or sine sine? Do y'all remember? For this, it's sine cosine, so cosine b, and then plus cosine a sine b. Is that familiar? Yes? If not, well, it's from a trig class. You can find it. All right, and so then this is going to become, that was just a little recall in our proof here. We're going to have the limit as h goes to 0 of sine a cosine, oh, sorry, sine x. Sine x cosine h plus cosine x sine h minus the sine of x all over h. Okay, and so now you're like, oh my God, what am I going to do? This still looks like a bunch of scary stuff. So how about, just for grins, I group the sine x's together. So I'm going to group this with this, right? That's allowed. So I'm going to write this as the limit as h goes to 0 of sine x cosine h. Okay, so if I group them, then I can actually factor the sine x out. So I'm going to factor sine x out. I'm going to get sine x cosine h minus 1 plus cosine x sine h. And I'm going to put this one over h. I'm going to put this one over h, right? That's all legal to do that. All right, now you have to think back to section I don't know, some section we proved, or I proved it in a video, what the limit as h goes to 0 of sine h over h is. Do you guys remember? Because now we're going to do a plug-in. Do you remember? What is this limit?
1.
Yeah, this goes to 1. And it turns out, you may have learned, or you could look on your calculator, I think it was also in the section, that the limit as h goes to 0 of cosine h minus 1 over h, well, actually, you should probably kind of convince yourself if you put 0 in here, it's going to be 1 minus 1 is 0. So this goes to 0, okay? So all you're left with is cosine x, right? In your limit. So this is going to be 0 plus the cosine of x, or the cosine of x. So you now know this is QED. Oedipus or Oedipus donus, or I don't know, quantum something something. So I done did it. Sometimes I put a little flower right here. Or a smiley face. Anyway, so that's a proof. We just proved that the derivative, so the derivative with respect to x of the sine of x is equal to the cosine of x. All right? You got it? Memorize it forever, ever, ever, ever. Okay? So it turns out then that we can get, when we know the derivative of the sine, we can use the same logic to find the derivative of the cosine. And once you know the derivative of the sine and the cosine, all of your other trig friends fall out using the quotient rule or the product rule. You know, you can find them no problem. Because of the relationship between, sorry, I put this down and now it's going to flip on me. Hold on. Because of the relationship between, like secant is 1 over cosine, and you know, that sort of thing. So you can find, and tangent is sine over cosine. So you can find pretty much everything else now. Okay, so without proof, I will tell you that the derivative of the cosine of x, the proof is very similar. F prime of x will be equal to negative sine x. So that's one you have to kind of remember, that it's negative. Students sometimes forget that. But you can prove that on your own for fun. All right, so now we have the derivative of the sine is cosine, and we have the derivative of the cosine is negative sine. So this allows us to take derivatives of more new and interesting functions. All right, for example, the function e to the x sine x. If we want the derivative of that, we should recognize that we're going to have a product rule. U, we will let be e to the x. So u prime is what, Robinson? What's the derivative of e to the x?
Hit it, Will.
E to the x. It's very exciting. All right, and if we let v equal sine x, what's the derivative of sine x? MCC? Cosine x. Everybody happy? Okay. So y prime, remember, the formula is u times v prime plus v times u prime, right? So y prime is equal to e to the x times the cosine of x plus v, which is sine x, times u prime, which is e to the x. And a lot of times we would, since we have an e to the x common to both terms, we would factor e to the x out. And we would get e to the x times cosine x plus sine x. Fun, easy, cool. All right. Now, on this problem, the next problem, you are going to have to, again, use not the product rule, but how about the quotient rule? The quotient rule, where this is your u and this is your v. So u equals cosine x. U prime is equal to negative sine x. V equals x. What's v prime?
1.
1. Good. All right. Now, what is the quotient rule? It's low d high, so that's v times u prime minus high d low, So that's u times v prime all over lo squared, which is v squared, right? Okay, so v is x, u prime is negative sine x, minus u, which is cosine x, times v prime, which is 1, all over v squared, which is x squared. Everybody okay? Lots of movement at Robinson. Everybody good? Okay, and so then this becomes negative x sine x minus cosine x. Uh-oh. No. Uh-oh. Tablet was closed. What? Shut up. Okay, sorry. Did I just yell at my computer? Minus cosine x divided by x squared. It knows it has me. Like, if it dies on me, I'll really be sad. I'll have to use, like, paper and pencil. Okay, what are the derivatives of the other trig functions? Prove them. All right, in my notes, it says this would be fun on a test. Which means that you might actually have to type in instead, and I'd have to look at it instead of, you know what I mean? Like, I'd have to evaluate your proof, so that could be time consuming. Or maybe I could make it take home. Or I could just be lying to you. I don't know. All right, let's just do one of them. I'll do one, for example. You can do some for me, too, later. Maybe tonight. You can have fun with one. If I did f of x equals the tangent of x, well, tangent, I know, is sine x over cosine x, right? So now, since I know the derivative of sine and I know the derivative of cosine, I can just use the quotient rule here to figure this out. I mean, it'll be a little bit of work, but I can handle it, right? That's my u over my v. So if I let u equal the sine of x, then u prime is, we just learned, cosine x. And if I let v equal cosine x, then v prime is negative sine x. Those were just proved a few seconds ago. All right, now I learned the quotient rule last time. It is low d high, so v times u prime, minus high d low, u times v prime, all over low squared, v squared. So that's my derivative. So this will be v, which is cosine x, times u prime, which is cosine x. I always get excited when I have like cosine x times cosine x. Because you know what's going to probably happen? Do y'all know? It's pretty exciting. U then I got a sine x and a v prime is negative sine x. Now I'm getting really excited because I've got a cosine squared plus a sine squared, and that's like my favorite identity of all time. All over v squared, which is cosine x squared. All right, so let's see if anybody's excited also. Cosine squared x plus sine squared x all over cosine squared x. Is anybody excited about the numerator? Anyone? Oh, they're pretty. I see you, Robinson. Don't think I don't know that you know that this is one because you are class president, not a geek, but class president. All right, cosine squared 1x plus sine squared x is equal to 1. I love that so much, I call it Big Daddy.
That's what I thought.
Yeah, well, you didn't say it. You got to embrace it. You got to throw it out there.
I don't want to be wrong. So.
Why not? Who cares if you're wrong? I'm wrong. I'm wrong like on recording. I've been wrong. I'm wrong all the
I
time.
say Big Daddy, but
You should have said it. It would have been so fun. It would have made me feel good, too, because you're the only one that really remembers Big Daddy, I think. Did anybody else have me? Oh, yeah. Yeah. Okay. Oh, that's right. So y'all just left me hanging. All right. That's Big Daddy. Cosine squared x plus sine squared x equals 1. 1 divided by cosine squared x is what? Anybody remember what? Right? That's secant. 1 over cosine is secant. So that's secant squared x. So all of this work for us to determine that the derivative of the tangent is secant squared x. Know it, love it, live it, be it. Okay? For the rest of your life, I call you when you're 75 years old and I'm like, 85. The derivative of the tangent of x is equal to, I don't know, let me fix my notation. The derivative of the tangent of x with respect to x, that's scary notation for the derivative of the tangent, is secant squared x. Okay? All right, now, should I do one more, or are you feeling, I'll do one more. You can sort of see that cotangent would fall similarly. It turns out, let me do like secant for you, so that's kind of fun too. So that's this one. Now, if I want to do, if f of x is equal to secant of x, then the derivative will be, let's see. Well, secant is 1 over cosine, right? So that is my u and my v. So u is equal to 1, u prime is equal to 0, v is equal to cosine x, v prime is equal to negative sine x, right? So if I want to find the derivative of the secant, I'm going to use the quotient rule. Low d high, so v times u prime, minus high d low, u times v prime, all over v squared. So that's going to be v, which is cosine x, times u prime, which is 0, minus u, which is 1, times v prime, which is negative sine x, all over v squared, which was cosine x squared. Okay? Everybody okay? All right, now this cleans up. That's 0. This is going to be sine x over cosine x squared, which will be sine x over cosine x times 1 over cosine x, right? And sine over cosine x is tangent, and 1 over cosine x is secant. So this is tangent x times secant x. But a lot of times you see it as secant x, tangent x. For some reason they put this, I guess they like to do in alphabetical order or something. So the derivative of the secant of x is secant x, tangent x. All right? So these aren't, they're not immediately intuitive, which is why you should stick them in your brain, or you could always have your trig sheet with you, or plug them in your iPhone or something. I don't know. But you're young, so you probably can fit them in there. All right. Although I will say sometimes some of the more obscure ones I have to think for a second. I know that the derivative of the tangent is secant squared. I know the derivative of the sine and the cosine. And then everybody else I can sit here for a second and come up with. All right. But hopefully you'll memorize them all. Here are a few of my favorite things. Raindrops and roses and whispers on kittens. Sines and cosines and, I don't know, Big Daddy. Functions. Favorite. I can't spell that word. When the dog bites. All right, so here's f of x, and here is its derivative. You will find this under the documents. I think I have a good derivative and integral sheet. It's a lovely, lovely sheet that has all of these on it. So you may want to look at that. That's under course documents online. All right, so if your function is sine x, your derivative is cosine x. If your function is cosine x, your derivative is negative sine x. If your function is tangent x, its derivative is secant squared x, right? And there's some more functions, right? Who's the friend of the sine? Well, cosecant is the friend of the sine, right? And the derivative of the cosecant is negative cosecant x cotangent x. I did that without proof, but you could prove it. All right. The friend of the cosine is the secant, remember, because it's 1 over cosine. And we proved that derivative is secant x tangent x. It's messy. And who is the friend of the tangent? The cotangent. And his derivative is actually negative cosecant squared x. So it's kind of similar to the tangent, but, you know, it's not the secant, it's the cosecant. And then, of course, my favorite, e to the x, likes to hang out, and he is e to the x. Now, we're still looking for ln x. You know, it doesn't feel complete yet. We'll get there. Are y'all happy? All right, so Robinson's leaving.
Gotta go. Bye, Miss
Goodbye.
Rose. Have fun singing.
Thank you. All right, now the rest of this is just a bunch of examples, which will be worth watching, Robinson, if you get a chance. All right, so all we're going to do here is just practice taking the derivatives using the only rules that we have, which are our product rules and our quotient rules, and that's pretty much it, the functions that we know. Like, so number 6 is pretty exciting because it's going to be a double product rule. We're going to have a product rule. It's here. It's fun, too, because I get to do it in multiple colors. We're going to have a product rule on this, but then we also have a product rule on here, okay? So I'm going to do the first one, u and v in red, okay? So u equals x squared, u prime equals 2x, v equals cosine x, v prime equals negative sine x. All right? Now, I'm going to come in here in green, and I'm going to do this one. This will be my u, and this will be my v. And you got to be careful with the minus. All right? U equals, I'm just going to not have the minus, but as I'm doing it later, I'll remember that it's subtracting this function. U equals 2x, u prime equals 2, v equals sine x, v prime equals negative cosine x. Okay? So now, to find the derivative. Well, this is just 2. When it's just a constant function, it just tags along. That's a good question. So I don't have to use the product rule because the derivative of 2 is 0, so one of the parts is going to fall out. So whenever you have a constant in front of a function, the constant just tags along. Yes?
Why is the v prime a negative?
So I was testing to see if you remember that. Good for you, girly. Right, the v is sine x, derivative of v is cosine x. Thank you for helping me with that.
The derivative of cosine x is negative.
Yeah, the derivative of cosine x is negative sine x. All right, we remember our product rule is u times v prime plus v times u prime. Okay, so for this one, so we can go ahead and do our derivative. It's going to be u, which is x squared, times v prime, which is negative sine x, plus v, which is cosine x, times u prime, which is 2x. And then it's going to be minus this next one, which is u, which is 2x, the green u, times v prime, which is the green sine x. Just kidding, the green cosine x. Plus v, which is sine x, times u, which is 2, and then plus 2 times the derivative of cosine x, which is 2 times negative sine x. Yeah, I'm running out of room there.
Wouldn't 2 have a derivative?
It's 0. So if you did the product rule with u equal to 2 and u prime equal to 0, then this one would fall out, and you would just have u, which is 2, times v prime, which is negative sine x. So you need to think of constants as just tagging along. Like if you have 5x squared, you don't seem to give me any trouble and want to do the product rule with that. But for some reason you do here. It's because cosine's not your friend? All right, well, you need to work on that. Okay, so anyway, this is plus 2 times the negative sine of x. So just remember numbers, when they're by themselves, they tag along. It happens in integrals too. Okay, so let's clean this bad boy up. This is negative x squared sine x plus 2x cosine x. Just feels better to me to do it that way. Distributing the negative here, ooh, look, minus 2x cosine x. That's cool. And then here, minus 2 sine x, and another minus 2 sine x. Well, this is going to be pretty. All right, and so this is its own animal. He just stays there, negative x squared sine x. But it's kind of fun because the 2x cosine x and minus 2x cosine x, those are going to cancel, right? And then these are actually the same animal, so I can group them up. And I have negative 4 sine x. Happy? Not really, because you realize how much work your homework's going to be. It's a lot of algebra, a lot of keeping everything straight. And you know what? Let me tell you something. If you try to go run a marathon this weekend and you haven't been training, it's really, really, really going to hurt. It may hurt even if you have been training. And so if you try to like take a test over this stuff without having done the homework, your brain could fall. It could explode. It could explode on the paper and it would be a real mess. So I really suggest that you go home and do your homework. And if you haven't, if you're behind on your homework today, tomorrow, you have got to get caught up because this stuff is not hard. I know it seems hard. It's not hard. It takes practice. It's not hard. It's new. All right? Every bit of math you've been doing since you came to this class was just math you had already learned and you were kind of reviewing it and adding a little bit. You have never seen what I've done right here. You have never seen, if this is your first time in calculus, you have never seen the quotient rule. You have never seen the product rule. You have never seen the derivative of the sign. And you're having to do all of that in one homework. Okay? So if you don't practice, you will be in for a significant challenge on the test. Okay. All right. Like that guy that ran the first marathon, he ran it and then he died, delivered the letter and died. So I don't know if you want to do that. You might want to run first. Conditioning is a good idea. All right. Here's my u, here's my v. So u is equal to 1 plus cosecant t. So u prime is equal to the derivative of the cosecant, which you can have your sheet there, or maybe your work on memorizing it. It's negative cosecant t cotangent t. All right, my v is 1 minus cosecant t, so my v prime is going to actually be positive cosecant t cotangent t. Everybody okay with that?
Do it on purpose with the t's and the A's.
Yeah, just to mess with your mind. Yeah. All right. So the derivative is, what's the formula for derivative using the quotient rule? It is high d low, so u times v prime minus low d high, v times u prime, all over v squared. Okay? All right. So u is 1 plus cosecant t. V prime is cosecant t cotangent t minus v, which is 1 minus cosecant t, times u prime, which is negative cosecant t. What, did I mess up?
Isn't it low D high or minus high D low? I mean, because you should be subtracted by u squared.
What?
I mean, it shouldn't be divided by u squared.
It's under low. This is the top's my u, the bottom's my v.
Yeah.
It's low squared.
Okay. Yeah.
High d low minus low d high over v squared.
Oh, okay. I thought it was low D high minus high D low. I remember it kind of.
That's what you'd say.
Yeah.
Well, it's what I'm looking at too on my notes. Crap. My problem is I never remembered the low D high. I mean, I never used it that way, and so I'm trying to use it. But did I do it wrong on this one too, or did I get it right on?
No, that one was right.
Which one did I get right? So, low D high. I'm sorry. Did I say high D low? I guess we
Yeah, you
could
said
watch
that.
it on the video. Incredible. All right, what is it? Lodi, V minus U. See, I just do it with the letters. I don't do the little song, but some students do this. All right, can I stop? I'm stopping the song. No more singing for me. Minus U. Don't quit your day job, Miss Brooks. All right, V times U prime minus U times V prime. I had other student, I actually always do dnd minus ddn. Derivative of the numerator times the denominator minus the derivative of the denominator times the numerator. That's how I remembered it. Somehow you have to internalize it. But what's really bad is when you finally internalize it and then you try to teach it another way. That's when it gets really tricky. Okay, V is 1 minus cosecant t times U prime, which is negative cosecant t cotangent t, minus U, which is 1 plus cosecant t times V prime, which is cosecant t cotangent t. Do we all agree? Am I doing this right now? I feel good. Okay, all over V squared, which is 1 minus cosecant t quantity squared. Okay, now, boom. I'm going to use a distributive property here. I get negative cosecant t cotangent t plus cosecant squared t cotangent t minus, distributive property here, yay, cosecant t cotangent t minus cosecant squared t cotangent t all over 1 minus cosecant t quantity squared. All right, let's see. Is there anything that cancels?
Yeah.
It does look like the cosecant squared t cotangent t will cancel with this, right? Now, these are the same animal. They're both negative, right? This and this are the same, and so I have two of those, right? So, some more room. I have negative 2 cosecant t cotangent t all over 1 minus cosecant t quantity squared.
Is it two cosecant?
You're so picky today. All right. I think I said t, but I wrote today.
I never really.
T for 2 and 2 for t. Okay. Was that fun? All right. Note to self. It doesn't happen to be helpful in this problem, but do remember, this is just notes, just remember, Big Daddy and his children are very fun and cool to remember. It didn't happen here, but they can happen sometimes, and so let's just make a little circle and put Big Daddy and his children in there. All right, Big Daddy is sine squared x plus cosine squared x equals 1, or the other way, cosine squared x plus sine squared x equals 1. And then I can never remember, I can't recall. I can never remember the children of Big Daddy, but I know the process. The process is to divide everything by either sine squared x or cosine squared x. So if I divide everything by sine squared x, I'll get 1 plus, because that would be sine squared x over sine squared x, cosine squared x over sine squared x, which is cotangent squared x, equals 1 over sine squared x, which would be cosecant squared x. That's one of the children. And the other child is to divide everybody by cosine squared x. Sine squared x divided by cosine squared x is tangent squared x, plus cosine squared x divided by cosine squared x is 1 equals 1 over cosine squared x, which is secant squared x. So not that it helped us in this problem, but because sometimes you can do some simplification with them, but they're good to have kind of in your brain, especially when you're seeing cosecants and squareds and that sort of stuff, because they may fall in and help you clean it up. All right, so you always want to have those at your disposal. Okay? All right, this problem would be better to be thought of as a cleanup first. This is a simplify first problem. Yes.
Wouldn't the numerator, the one on the bottom of the fraction.
D down, denominator.
Denominator, yeah. Wouldn't that be a negative cotangent squared? No, the whole thing is squared. Because I was thinking, yeah.
Right here? Yeah, there's nothing really, I mean, you could multiply that out and get yourself in trig Hades, but it's really not,
I was
nothing, yeah.
One squared, because if you do 1 minus cosecant squared x
Yeah.
equals negative.
Yeah, but because of the squares on the outside, you can't do that.
When you square 1, it's still 1.
Yeah, but you always have a middle term, remember? When you FOIL it,
yeah,
you would have had, and it would have messed it up. Okay, simplify first is my trick on this one. Remember, whenever you're dividing by a monomial, even if it's a funky trig monomial, it's nice to think of it that way first. So the function, I'm going to think of this as sine q over cosine q plus cosine q over cosine q, right? And that's really nice. I haven't done anything yet. I haven't taken a derivative, but sine q over cosine q is tangent q, and cosine q over cosine q is 1. Y'all with me? So the derivative, p prime, the derivative of the tangent is just secant squared, and the derivative of 1 is 0. Okay? So there you go for that one. All right, now let's do the next one. Find dp dq if p equals that. All right, again, this is going to be one that is probably, it's better not to multiply it out. You can actually think of this as two functions, and you can use the product rule, where this is your u and this is your v. So u equals 1 plus the cosecant of q. So u prime is equal to, the derivative of 1 is 1. The derivative of cosecant is negative cosecant q cotangent q. All right, v is the cosine of q, so v prime is negative sine q.
Derivative of 1 is 0, right?
Yes.
Okay, you said derivative of 1 is 1.
Yeah. Sorry. The derivative of 1 is 0, which is why I didn't write it. Okay. So, and what's our formula? It's u times v prime plus v times u prime. All right. The derivative of p with respect to q is u, which is 1 plus cosecant q, times v prime, which is negative sine q, plus v, which is cosine q, times u prime, which is negative cosecant q cotangent q. Everybody okay? It's weird. These q's look weird, don't they? All right, and so then we will distribute out here. This is going to be negative sine q plus, or there'll be minus cosecant q sine q plus minus cosine q cosecant q cotangent q. Now, you should realize that there's going to need to be some significant cleaning on this problem. And so, are you happy, Courtney? You seem to be smiling. I love trig. I can't wait to be a math teacher and get to teach trig all day long. The sine of q minus cosecant q is 1 over the sine of q times the sine of q. Maybe that's what she was excited about, because there's some canceling going on there. Mine is pretty cool. Minus, this is cosine q. Like, my son the other day, he was working on a problem, and it was a parallel perpendicular. It was like, determine if the lines are parallel, perpendicular, or neither. And he did it, and he found one slope was 2 and the other slope was negative 1/2. He's like, yes, they're perpendicular. Because I guess if they had been neither, it's always so disappointing. You know, neither's, it happens, but it's no fun. Okay, cosecant is 1 over the sine of q, and cotangent, what's cotangent? It's cosine q over sine q. Okay, so let's see what we got. We can cancel this, so that's going to be minus 1. This is kind of fun because you're going to have cosine squared q over sine squared q, right? Right. So we have this negative sine q, and we have the minus 1, and then we have minus cosine squared, I'll go ahead and write it, q over sine squared q. But we remember that that's cotangent. So watch this. I can write this as negative sine q. Now, if I'm feeling crazy, I can factor a negative out. So I'm going to do minus parenthesis 1 plus cotangent squared q, right? Now, who is that? That's one of the children of Big Daddy.
Cosecant squared.
This is cosecant squared in here. Does everybody see what I did? I rewrote this as cotangent squared q, and I factored the negative out. Okay? And so then that is negative sine q minus cosecant squared q. So, who would have thought? Who would have thought the derivative of that function was that? Okay. Now, why are we doing this? Maybe that's your question. The reason why, this is a short lesson. Lots of juice. All right, the reason we do this is to find equations of tangent lines. That's one reason. Velocities, accelerations, functions can be defined with, situations can be defined by trig functions, and we need to find their rates of change. And we need to find the instantaneous rate of change, and the change rate of the equation of the tangent line is a wonderful tool. So we will do that on this problem. Find the equation of the tangent line at the point pi over 2, 2. Also find the point on the curve where the tangent line is horizontal. Okay. All right. So to find the equation of the tangent line, we first need to find the derivative. So if y equals 4 plus the cotangent of x minus 2 cosecant x, the derivative of 4 is 0. The derivative of cotangent we learned is negative cosecant squared x. The derivative of the cosecant we learned is negative cosecant x cotangent x. So this is going to make this plus cosecant x cotangent x. And that's on your sheet. All right, now to find the slope at the point pi over 2, 2, what we'll do is we will plug x into this equation, and that will give us the slope. So the slope at the point is m equals negative cosecant, I'm going to do it like this, pi over 2, and then you square it, plus 2 cosecant pi over 2 cotangent pi over 2. All right, now you have a unit circle, you have a calculator, maybe you even have a brain that can tell you the cosecant of pi over 2. Cosecant is 1 over the sine. Pi over 2 is 90 degrees. On the unit circle, the y coordinate at 90 degrees is 1. So this is going to be, actually my negative should be on outside here, because we're doing the cosecant squared and we take the opposite. So this is going to be 1 squared, which is negative 1. So the opposite of 1 squared, which is going to be negative 1, plus 2. I just told you the cosecant of pi over 2 is 1. The cotangent of pi over 2, cotangent is cosine over sine. The cosine at pi over 2 is 0. So it's 0 over 1, which is 0. So your slope is actually negative 1. So the equation of the line is y minus y1, which is our coordinate, that's 2, equals m, which is negative 1, onto x minus pi over 2. And so we get y minus 2 equals negative x plus pi over 2. And so the answer that you type in is just y equals negative x plus pi over 2 plus 2. Kind of a weird graph that. It's kind of funny to think, how are you going to graph it? Like, how are you even going to divide pi by 2?
1.07.
Pardon? Yeah, you can tell me, you can give me an approximate value, but you don't know what it is exactly, right? So you can spend your whole, and then you can, how could you graph it if it's always continuing on? I know, but don't irrational numbers just kind of freak you out every now and then? Or you guys are just, you're a bunch of engineers, you're like, whatever, 3.14, move on, Miss Brooks. Just 3, just use 3, I don't care. Okay, all right. The tangent line, where I'm going, I mean, at night, sometimes just think about the square root of 2. Like, I just think it's so weird. The tangent line is horizontal when m equals 0, right? The slope equals 0. Or here, when the derivative equals 0, right? So what was our derivative? It was negative cosecant squared x plus 2 cosecant x cotangent x. Was that our derivative? I don't remember that. Yes, it was. Okay. And that needs to be set equal to 0. Well, this is going to be fun. All right. Why don't we factor a cosecant x out of that? Because whenever you're trying to solve an equation, factoring is always a good idea. So cosecant x factors out, and we're going to get, we'll have one left here, negative cosecant x. And it might, it doesn't, it's a good idea just to, I don't know, you don't have to, but I'm going to factor negative cosecant x because I like to be positive here. So this is going to be cosecant x, and then this will minus 2 cotangent x equals 0. So we need to figure out where negative cosecant x equals 0 or where cosecant x minus 2 cotangent x equals 0. Okay, and so this is saying where does negative 1 over sine x equal 0? Anybody have an idea? When can a fraction equal 0? Well, only if the numerator were 0, right? But the numerator on this fraction is negative 1. It'll never be 0. So you can try all day long for this to be equal to 0, but it won't be. The other way you could think of it is the graph of the cosecant. I don't know if you have it in your head, but it's that one that looks like, it's a bunch of u's, like there's some u's here, and then there's this part. You remember it? Sort of like that. Yeah? It had the asymptotes. So it never crossed the x-axis, which is what would be necessary here for this to be true. So it never crosses, so this is no solution. All right, well, that was good. So it must be this bad boy over here that we can work with. Okay, well, let's see. Cosecant is 1 over the sine of x. Cotangent is 2 cosine x over sine x. Well, that's nice, because we could write this as 1 minus 2 cosine x over sine x, right? We've got a common denominator. Right, now when I ask you when does a fraction equal 0, that will be where the numerator equals 0. So I will do 1 minus 2 cosine x, and I will set that equal to 0. And I will solve this, and I will ask myself, when is the cosine x equal to 1/2? Because I moved the 1 over and divided by negative 2. And there are lots of places where the cosine of x is equal to 1/2. Do you guys remember? Can you tell me one? Mm-hmm. Good. This is true when x equals pi over 3 plus the period of the cosine, which is
Pi.
a little more.
2 pi.
2 pi. And in this case, it's going to be 2k pi, where k is an integer. Meaning, if I were to add an entire rotation, say k were 1, if I add an entire rotation, that would be, I would get back, that I would be at, entire rotation is 2 pi over 3, so that's 7 pi over 3. That would be another place where cosine x equals 1/2. If k were 2 pi, that would be 2 rotations, and I would be back at a version of pi over 3. If k were negative 1, If k were 0, I'd be at pi over 3. So k isn't, this is, Zahlen is German for integer. And so we use the z to represent integers, to mean that k is contained in the integers. All right, but there's another place where cosine x equals 1/2 on the unit circle. Do you remember? You were right here at pi over 3. You had 1/2 comma square root of 3 over 2. And this was your cosine. And that was at the angle pi over 3. What was the other place? It's over here. No, it's not. It's over in this quadrant.
5 pi over 3.
Yeah, all the way around here, 5 pi over 3. You have 1/2, and then negative square root of 3 over 2. So this is also true at x equals 5 pi over 3, and as many times as you want to go around a complete rotation. So that's why you would put the 2k pi there, because that means that it'll get you, there are infinitely many places where it is true that the cosine of x equals 1/2. So you have to describe those places, which is what I'm doing with that k element of z thing. K is an integer. Are you all okay? Okay. So that tells you that there's lots of places where this graph has a horizontal tangent line, infinitely many places. And this is where this is the pattern that describes where they occur. Oh, wow, that was a lot. That was a lot today. Lots of trig. All right. Okay, that's it, though.